I will begin. Dear Father, we thank you for this day, and I just thank you for these students and their diligence. Help us to use this time wisely, Lord, to glorify you. In your name I pray, Lord Jesus. Amen. So today, we start my chapter 3, which is on ordinary linear differential equations. So I have a little bit of sort of general, well, not sort of, but rather general theory to share with you, some of which I will write on the board, most of which I will project, because these are really things that we need to be more aware of than, I mean, these things I'm telling you, they certainly influence our calculation, but they don't really tell you how to solve problems. They tell you, well, that's not true. They do tell you how to solve problems. They sort of help focus our efforts and give us confidence that what we're doing is complete, all right? And the terminology that I'm introducing here is important, so let's get to it. Linear differential equations. Let me state the general problem. Let I be an interval. What's an interval? An interval is a connected subset of real numbers. So it could be the whole real line. It could be like an open interval, a closed interval. That notation is consistent. But for most part, we either have the whole real line or like some sort of open set, possibly to infinity, possibly to minus infinity, something like that. In other words, the larger point is that the domain of definition here is some connected domain. All right, that's kind of important. So some connected subset of real numbers, such that, and we got these component functions, a0 through an, such that the 0th component function of x is identically non-zero for all x in I. So we want to assume that the 0th component function is non-zero for every point in the interval of the interval which defines this differential equation. Given all this, and these can be functions, okay? These can be functions, these a sub zeros. And then here's the deal. We have a sub 0, dn y dx to dx, the nth derivative of y with respect to x, plus a1 d to the n minus 1 y dx to the n minus 1 plus plus a to the n minus 1 d y dx plus a sub n y equals to f. All right. The numbering of the coefficients is not absolutely written in stone. I think I stick with this nomenclature for this section of the notes, but like I could, on a different day, if I hadn't been looking at my notes, it would not be at all surprising if I had numbered them like an minus 1, a0. That would not be surprising to me, right? So you could number them a different way if you wanted to, but once you make a numbering, you got to stick with it. So I'm sticking with this because it's what's in my notes, all right? Now, so that is an nth order linear differential equation on I with coefficient functions a0 through an, and the forcing function is f. So this right here is nth order linear ODE, right? In dependent variable y and independent, unfortunate spacing, with dependent variable y and independent variable x. All right. Again, these guys these are the coefficient functions. Coefficient functions. We call the function f this guy. This is the forcing function, aka inhomogeneous term. All right. Some further language terminology, okay? If A0, A1, AN, if these are just real numbers, then I need to give this stupid thing a name. Let us call it star. Right? Then star is a constant coefficient. Nth order problem, yeah. The lion's share of our efforts in the next week or 3 or 2 or something like that, I forget, for a few classes, we'll be working on how to solve the constant coefficient problem. All right? It's actually pretty easy. After the dust settles, it's actually pretty easy. If the forcing function is identically 0, then star is homogeneous. All right? Now, there's other notations that I should mention. We like to use operator notation. So here, d acting on y is dy dx, and sometimes we'll also write that as y prime. So big D is differentiation with respect to the, independent variable. What would d squared y be? What on earth is this? Ooh, not cool. Not now, not ever. I've opened the Firefox virus on my computer. I mean, Firefox. To me, that's a virus because I don't use it. It's trying to put Bing on there. I don't care about Bing. Let's see here. So what would d squared y be? You guys, this is not a hard question. I know you guys are too distracted by the oncoming hurricane to focus on your schoolwork right now, but no? Fine. D squared y, what that means is d of y, which of course we have 2 different notations for. We could say that's d squared y dx squared, or of course we could say y prime prime, right? So star, we can restate star. In fact, star can be restated as L acting on y equals to F, where L is equal to, what is L? If you look at this boxed equation, right, what you could do is pull out the y to the right and look at that whole thing as, say, oh, finally, it's about time. Let's see here. So A0, see, it was worth coming today. All right, A1 d to the n minus 1 plus plus an minus 1 d plus an. This whole thing is an operator. This operator acts on y and it spits out f. So we can look at this thing I just put in parentheses. This whole animal, this is the L. All right? So this can be restated as L of y equals to f, where L is equal to a0 d to the n plus a1d, an minus my stupid numbering, an minus 1 d plus a sub n, like that. Yeah.
Around whatever the operator's acting on, are those brackets or parentheses, or does it matter?
Those are parentheses, but we try to write square brackets for the input of operators. Like, that's just a notation. It's not, it's a common notation at this level of math to use the input of an operator to put it in brackets. Like, so that's why I tried to put like bracket y. But you could reasonably put parentheses. It wouldn't be wrong. It's just that. So like a similar notational issue in Calc 3 is like, students ask me, is it parentheses or is it, the angly brackets? Like, which is it? And the answer is yes. They're really just a choice of notation to emphasize things. So the angle bracket emphasizes it's a vector. The parentheses emphasizes that it's a point. But I add vectors and points freely. And in the same kind of way, you could use parentheses or you could use brackets. It's just a question of emphasis. This emphasizes that D is an operator. It's acting on the function y. Operator, what an operator is it's a function-valued function of functions. What to say that? What I mean is that you take a function, you stick it into an operator, and out pops another function. So an operator takes in functions and outputs functions. You've already been dealing with operators. I've been teaching you, since Calculus 1, you've been dealing with operators. Differentiation is an operator, right? So, actually, it's not just any operator. It's what's called a linear operator. So, theorem, definition rather. L is linear operator if L of C1 Y1 plus C2 Y2 is equal to C1 L of Y1 plus C2 L of Y2. So linear operators break up across addition, and they allow us to pull out scalar multiplication. Do you know any examples of linear operators? I mean, that's certainly true for the derivative, right? If I take d dx of c1 y1 plus c2 y2, I have c1 d dx of y1, right? Plus c2 d dx of y2, yeah? And that's true for all functions y1 and y2, for which we can operate on, right? Differentiable functions. So the derivative is a linear operator. What else is a linear operator? Yeah, integral. Well, see, I guess I got to be careful. What's the output of an integral? I mean, linear. The integral is linear, but its output would either be a number or, yeah. I mean, but it does have linearity. I agree. Just like the limit. The limit also is a linear thing, right? But anyway, certainly derivative is linear. What else? Very, very connected to derivative is linear. How about second derivative? Is that linear? It is, right? The second derivative is just, so this is also an identity, which is true. The second derivative is linear. In fact, I could erase that too and put an n, or let's say k. The kth derivative is a linear operator, right? If you differentiate k-fold times. This is an identity which we know from, in fact, Calculus 1, right? Another fun fact of linear algebra, linear combinations of linear operators are linear operators. You're like, what on earth are you talking about? Well, try it out. So if I have like B1L1 plus B2L2, right? Where L1 and L2 are themselves linear operators. What happens when I let that act on a linear combination? Like what happens there? So let's let it act on C1Y1 plus C2Y2. Let's see what happens. So by definition, when we add operators, how does that work? We just add them just like we add functions by components. Like so, the rule, the definition for adding two operators is just like the rule for adding two functions. We just add the outputs, pointwise defined. So that's actually the definition of how we add two operators. If you'd like, I can be more abstract about it. If we have operator S plus operator T, and that acts on a function, well, that's just by definition S acting on the function plus T acting on the function. So this is how we add operators, just by pointwise. Right? This is the rule for adding operators. Composition of operators, on the other hand, multiplication, S times T of F, well, that's S of T of F. So that's what multiplication means. That multiplication of operators is actually composition. This is not new. This is what we mean by second derivative, right? d dx squared is d dx of d dx. It's already that idea, right? This is not a new idea. Maybe it's a new notation. All right, getting back to my linear combination of linear operators is a linear operator argument. What's next? We're assuming that L1 and L2 are linear, right? So that gives me B1, C1, L of Y1, plus C2, L of Y2, plus B2, parentheses, C1, L of Y1, plus C2, L of Y2. And, tired of this red, let us regroup things. We've got B1, C1, plus B2, C1, all times L of Y1, group all those terms together. And I've also got B1, C2 plus B2, C2 acting on L of Y2. I can group all those together. And let's see here. Oh, I think I'm supposed to have I've lost my numbers. Look at this. Which one was this? In fact, I think what I wrote in purple is nonsense because I lost my numbering, right? Sorry about that. Oops. Sorry. See, this was kind of important. That 1 goes here and here. This 2 goes here and here. So let's see here. I have B1, L1 of C1, Y1 plus C2 sorry guys, I got a lot of flavor options here. I got to think about what I want to get to. Let's factor out a C1. We've got C1 times what? C1 times B1 L1 of Y1, right? Where else is a C1? Over here, right? Plus B2 L2 of Y1. That's everything with the C1. Now the C2, what do we got? I've got a B1 L1 of Y2 plus B2 L2 of Y1, yeah? I think that's good. That should be a 2, shouldn't it? This is a 2, isn't it? This is a 2, right? Two. C2, B2. What is it? Yeah. Now the reason I'm doing this is to just say, okay, so that's really C1. I will get to the point here eventually, guys. So this is C1 times B1L1 plus B2L2 acting on Y1 plus C2 B1L1 plus B2L2 acting on Y2. And that shows what I'm trying to show, which is that if we think of this as being an operator, let's say T, what we have shown, what this calculation shows is that T of C1Y1 plus C2Y2 is CT of Y1 plus T of Y2 times C2, which shows you that, in fact, this T is itself a linear operator, which was my claim. If we take a linear combination of linear operators, we have a linear operator. Does that, I'm sorry, I stumbled a little bit in reorganizing things, but I mean, if this was a question on the next quiz, you'd be like, thank you, right? I mean, it's easier than what you're doing right now, I think. But now you put this together, right? We have two things. We have that the kth derivative is a linear operator, right? For any k. We have that a linear combination of linear operators is a linear operator. If you can do it for two things, you can just as well do it for 3 or 4 or 5 or 6, right? So put that all together, this L, right, is a linear operator because it is a linear combination of linear things, is it itself a linear operator. So that's the takeaway from this, is that the L, so here's the theorem, and I'll write it this way, the L in star has L of C1Y1 plus C2Y2 equal to C1 L of Y1 plus C2 L of Y2. And, you know, if you want me to be greedier, I could be greedier. And in fact, we have L of the sum, I equals 1 to n, of Ci, Yi, is equal to the sum, I equals 1 to n, of Ci, L of Yi. Generally, this is linearity for n things, okay? It says we can pull constants and sums apart with a linear operator. So what does this say about the linear differential equation when it's homogeneous? So think about this. If star homogeneous, right, then we have L of y is equal to 0 is star, right? That's the differential equation we're trying to solve. And so a homogeneous differential equation is really nice because we have a theorem that is almost immediate from this bit of algebra we just did, right? Theorem, if L of yi equals to 0 for I equals to 1 to ... n, then guess what? Y equals to a sum, I equals 1 to n of Ci, Yi solves L of y equals to 0 for any choice. For any choice of constants, C1, C2, Cn in the reals. Let me put it into words. The linear combination of solutions to a homogeneous problem is, again, a solution to the homogeneous problem. Now, let me make this a little bit less abstract here for a second, just so I don't lose you. For example, of this, we've thought about y prime prime plus y equals to 0, right? That's a differential. That's a constant coefficient problem. It's homogeneous. What's the L? Let me do some name calling here. Constant coefficient. It's homogeneous. The L, quote unquote, here is d squared plus 1. That's the operator here. We've even worked out that a solution to this has the form what? Well, we have noticed before that both sine and cosine are separately solutions, right? It's like y1 equal to cosine. Now, I guess the question is what prime mean. What does prime mean? This is ambiguous, right? What's the independent variable here? It's not been written, has it? In this example, it has not been written. So the question is, what does y prime mean? You guys give me a meaning for y prime. Two popular choices, dy dx or dy dt. Which one do you want? X, all right. So that has to be stated somewhere. Otherwise, there's not a unique answer, presentation of the answer at least. But anyway, so then cosine of x is one solution, right? And how about sine of x? That's another solution. These are both solutions to the homogeneous problem that we've stated, because if you twice differentiate sine or cosine, you get back minus sine or minus cosine respective. And so when you add them to y prime prime, you get 0. This theorem that I just wrote in purple above it says that any linear combination of sine and cosine is a solution as well. What do we mean is a solution to y prime prime plus y equals to 0? What does that mean to say something's a solution to a differential equation? It means that if we take that quote-unquote solution and plug it into the differential equation, the equation holds true, right? I could be more formal about it, right? If we have L of y equals to f, and to be more specific, L of y of x equals to f of x for all x in I, which is the domain of definition of this linear differential equation, then y equals to, well, phi defines solution to, let me call this thing star again, Q star, provided that L of phi equals to f, well, I mean fine, of x equals to phi of x for all x in the domain of interval, domain of definition. There you go. But all that says is that if you plug the formula for y equals to phi, into the differential equation, and you do the linear operation of L on it, out pops f, out pops the forcing function. Bingo, it's a solution. Yeah? Let me just pause for a second here and talk about applications. If you think about the logic here, it's kind of backwards of how we think about physics, right? If you think about a spring, for example, if we think about a spring, you know, and a mass attached to it, then we have F is equal to minus kx, right? Hooke's law, and that's equal to mx double dot. Or if you like, mx prime prime. This is Newton's second law. So you see mx prime prime plus kx equals to 0. This is a second order constant coefficient differential equation, right? That's the mass spring problem, right? It's homogeneous at the moment, it's just oscillation. But what happens if you add a force? I mean, logically, if you think about it, you know, if we imagine some guy pulling on this system, nudging it back and forth, right? Oh, wasn't trying to give him a Pharrell hat there, top hat, there we go. He's got a stick, and he's like, Then where does that appear in this? Well, that appears, we've got MA is equal to F net, right? So now it's minus KX plus force external. And so then the equation becomes MX prime prime plus KX equals to F external. So I just point out there's something kind of funny here. If we think about it physically, you know, you basically, once you have the spring mass system, you think about the external forces producing the motion, right? But the process of solving the differential equation is kind of opposite of that, isn't it? I mean, if I draw a picture, here's the differential equation is operator L, right? I'm trying to find a y to plug into the L, and out pops L of y equals to the external force, you know? So I need to find how this L works to produce the external force. But physically speaking, I think about being given the external force as to produce the y, right? So what we're actually interested in some sense, in terms of physics, is the inverse of L, whatever that is, if you wanted to think about it. That's just a comment. So we want to learn how to actually unravel these, how to solve for y, given a choice of L, right? Given a differential equation, and given a forcing function, how do we actually find the solution, right? And like here, is this it? Is there more? Is this the general solution to this problem? Is there more? What do you think? Is this everything? Do you guys have an intuition for it? If you start thinking about a spring, this would be like m equals to 1, k equals to 1, mass 1, spring constant 1, spring mass system, right? It does seem like this should be everything, because if you think about it, you just got simple harmonic motion back and forth, right? This is a complete mathematical description of that. If I make x be time instead, it would make more sense, maybe, yeah? If I erase this x and put a t here, that just puts a t here, and that puts a t here. I do test on this, guys. And usually you guys have been getting it pretty well lately, but I got to a saturation point where students would write answers in terms of x or t, where I'd ask the opposite at the start of the problem, and it grew to offend me, so I began testing on it. So I'll say things like, solve y prime prime plus blah, 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 where y prime equals to dy dt, or where y prime equals to dy dx. And if you give me an answer that has independent variable as it ought not be, I fuss, because it's kind of important. Anyway, because your boss would be very confused if you gave him a formula where x was playing the role of time, and you're also using x as a position somewhere else. You could see how this would lead to confusion, right? So which is space and which is time for like the letters in your model? It could matter, documentation being clear and stuff like that, right? All right, anyway, enough. So what I'm going to share with you next is the general theory of this, okay? So, I've described to you that if we have a few homogeneous solutions, we can take a linear combination of them and build a new homogeneous solution. But the larger question is, like, what is the general solution for the linear problem? What does that look like, and how do we understand that? So to understand it, we need a couple more concepts. I've already actually introduced to you, believe it or not, the concept of a span. In linear algebra, about half of the time we're talking about spans. About half of the time we're talking about linear independence. A linear combination is a span. This right here is a span of the sine and cosine function. This is a span of y1 through yn. Linear combinations are spans. So I've already introduced to you the idea of a span. That part of it is here. But the other idea is linear independence, right? Linear independence is the idea that the solutions are genuinely different, right? Like if Taylor gave me sine of x and what's your name? Grace. If Grace gave me twice the sine of x, I'm sorry, I should know by now. My apologies. You know, if Grace gave me sine of 2 times sine of x, I'd be like, I'm sorry, I already have sine of x in my collection. Your contribution is worthless to me. Oh, I'm sorry. That's very. I would still value it, but it wouldn't add anything new to the solution. You know, I mean, sine of x and twice sine of x, they're the same, kind of the same function as far as differential equations is concerned, right? So we need to find some way of describing when functions are genuinely different, and that's what linear independence is. It gives us a notion of distinctness of functions. So. So I'll get back to that. I'm going to do things in the order that they're in the notes, but eventually I'm going to come back to that linear. I have the definition of linear independence here, about a page or two. We'll get to it. I think that's everything. Yeah. Okay, so this is the big theorem that drives everything past this point. Is the existence and uniqueness theorem. And here it is, in all of its glory. It's not terribly important that you write it down. It's fine that you're not writing it down right now, but you do need to understand what it says. All right, so let's try to focus on that. What does it say? So the preamble basically says we're looking at a linear differential equation with coefficients as I laid them out. They have to be, you know, nice enough functions of x as I'm using. I'm using x as the independent variable at the moment. So we've got a bunch of continuous functions on an interval I. The leading coefficient's non-zero. Then here's the theorem. There exist, and we're also given, and this is an initial data set. So here, y1 through yn minus 1, these are not the solutions I was just talking about. These are actually given values, real numbers, fixed real numbers. Think of it as an initial set of data at time x naught, if you will, or position x naught. Then there exists a unique function phi, such that we can basically plug it in to the differential equation, and it works, right? In other words, phi is a solution to L of y equals to f. And more than that, this solution fits the initial data in the sense that phi of x naught is y naught. Phi prime of x naught is y1. Phi n minus 1 of x naught is yn minus 1. So this is the initial, the existence and uniqueness theorem. The proof of it rests on some fairly, well, not that delicate, but pretty famous analysis. It's you prove it with a fixed point theorem. There's an iterative method which is used to solve it. In fact, it probably wouldn't be too far off topic for Dr. Wang to solve this, to actually prove this in numerical methods here. I don't think he probably does it, but he gets awful close to it, if I had to guess. Because it involves the contraction mapping principle. And anyway, that's not this course, right? This is not an analysis course. We're just going to use that. Here's a couple of examples of it actually being, you know, fleshed out. In some of these, you already have the technology to do, right? Y prime equals to y, you separate, you integrate, right? Like dy dt equals to y, dy over y equals dt, integrate both sides, do some algebra, you get y equals e to the, oh, I can't read. I thought that x was a t. That is an x. I definitely need to be wearing these. Sad, but true. So the point is that is a solution to this. And this is easily recast as y prime minus y, right? So this is just a linear homogeneous problem in disguise. Because you can move y and all of its derivatives on one side and get all of that stuff as equal to 0. That makes it homogeneous. And so, you know, in this case, the coefficients are constant. They're both 1. That's one solution. And you can pick any, if you want y of, you know, if I want, for example, the unique solution with y of 0 equals to 1 is that one. But if you told me that y of any particular value of x was something else, I could put a coefficient in front of the exponential and make that happen. That's all right. Here, y prime prime plus y equals 0. If I want y of 0 equal to 1 and y prime of 0 equal to 1, I could get that by putting y equals cosine plus sine, right? This is just a token example. The theorem says that it doesn't matter. In fact, this 0 is playing the role of x naught. First of all, that 0 could be any real number. You could be given an initial position and velocity at any real number, and any position and any velocity at that time, right? If we think about the independent variable being time. And there is a solution which fits that initial velocity and that initial position at that time. That's the existence and uniqueness theorem. All right. Here's another example which is a little bit weirder. This time, the interval, is actually 0 to infinity. So this one's not constant coefficient, and you can see that the leading coefficient would be 0 if x is equal to 0, right? So 0 is definitely not in our domain of definition for the differential equation. The natural domain would be like 0 to infinity, or you could do minus infinity to 0. Either one would actually be okay here. But it turns out that that's the solution. Now this we definitely don't know how to derive at the moment. That's just dark magic that I've written this down, right? So anyway. Now this one is an nth order problem that you can already solve. How do you solve y prime 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 equal to 0? Integrate once, then you get y prime 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 1 less equal to a constant. Then integrate again, you get c1 times x plus c2 is equal to the 2 less derivative. Just keep integrating once, again, and again, and again. If you integrate n-fold times, you'll get a solution that looks like this. I mean, technically, if you directly integrate, you'll also have like fractions. Like this would come with a half, and the next one would come with a half times a third. But anyway, that's the solution to the nth order problem. You can solve just by straight integration n-fold times. And that actually, that solution we just looked at says a lot, because that's the general solution to y prime 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 equal to 0, right? It has n arbitrary coefficients in the solution, and it's built with the functions 1, t squared, dot, 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 t to the n minus 1. If you think about those functions, they're really different. They're independent. There's no way you can get the graph of t from the graph of 1, or the graph of t squared from the graph of t, or t cubed from t squared, right? Those polynomials, monomials, those are independent functions intuitively. So there's something to be seen from that example. It actually illustrates the general story. All right. Anyway, but first, a definition that I've been promising: linear independence. So what do we mean by linear independence? A set of functions f1 through fm are linearly independent on the interval I, if and only if. This means it goes both ways. I mean, this is the definition. If whenever you have c1 f1 of x plus c2 f2 of x plus plus cm fm of x equal to 0, for all x in the interval, implying that the coefficients must all be 0. Right, so this is a function I mean, I could erase the x's from this and just like write c1 f1 plus c2 f2 plus dot 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 cm fn equal to 0. That would be like a function equation. What does it mean when you have two functions are equal? It means that their outputs are equal for every possible input, right? So a function equation is actually infinitely many scalar equations if the domain is interesting. So this is a lot of data. This linear combination equal to 0 for all x in the domain of definition. And that's what makes this kind of linear independence more interesting than the one we study in linear algebra. In linear algebra, we typically talk about R2 or R3 or finite dimensional vector spaces. And there's none of this for all x in the interval stuff. That makes those problems easier to think about. It also makes them problems that we can't use calculus on, so they're boring. Wait, no, it's linear algebra, it's not boring. We love linear algebra. But anyway, I'm just telling you that the linear independence of functions is a little bit fussy. But it's okay. I will show you how we deal with it here shortly. On the other hand, if it's not if this equation set equal to 0 does not imply that all the coefficients are 0, all right? If it implies that one of the coefficients is non-zero, then that means they're linearly dependent. And since we're working with a field, which means every non-zero thing has a multiplicative inverse, it follows that you can solve the linear, this dependence up here. You can solve this equation for one of the f's. You can express some jth function as a linear combination of all of the remaining functions. And that's what we mean by linear dependence. Fj is a linear combination of f1 through fn with j removed. So it's redundant, right? We've already got this function from all these ones. We don't really need it. We can throw it out. It's linearly dependent. It's not what we want. We want independent functions. All right. So it's useful to have a criteria. It's useful to have a criteria for testing for linear independence of functions. That criteria is given to us by what's called the Wronskian. Let me derive it for you. Here's the derivation. So if we have linear independence of functions on I, that means that this linear combination is equal to 0 for all x in the interval. But if this equation is true for all x, we can differentiate it. Differentiate this equation, you get that equation. And that's true for all x. But if we can differentiate it once, we can differentiate it twice. And we can keep differentiating. And so we get not just one equation, we get a bunch of equations involving the functions and their first and second and so forth derivatives, eventually the m-1th derivative. Put these all together, we have m equations and m unknowns, C1 through Cm. We can repackage this as a matrix equation, like so. And so we've got this matrix of functions and their derivatives times that constant vector, C1 through Cm, equal to 0. Linear independence says that we are forced to have all of these be 0, which means that this system of equations has a unique solution of just the 0. That means that this coefficient matrix must be an invertible matrix. Or more precisely and usefully for you guys, it must have determinant 0. Excuse me. Determinant what? Non-zero. Invertible matrix has determinant non-zero. So the determinant of this matrix is what's called the Wronskian. If the determinant, if the functions are linearly independent, then the determinant of the Wronskian, well, I got to be careful here. Yes, if the functions are linearly independent, then the Wronskian is non-zero. That this calculation shows. And here it is, the Wronskian of y1 through im. You just put the y's in the top row, first derivatives, da-da-da, m-1 derivative. There you go, that's the Wronskian. We can test linear independence of functions. Can you hit the other lights for me for just a second? Thanks. Here, before I go on with this general jibber-jabber, let's just stop and calculate the Wronskian of, let's do something relatively simple. How about cosine, cosine t, sine t, and of course the variable t, right? So that's the determinant. So I got my cosine t, sine t, and then I differentiate to get the second row, right? So what's this work out to? You got yourself cosine squared minus sine squared t. So the Wronskian for cosine and sine is 1. That proves, in fact, that cosine and sine are linearly independent functions. For cosine and sine are linearly independent. Let's calculate the Wronskian of 1t squared, right? That's a 3 by 3 determinant. We put 1t squared, differentiate again. What's the Wronskian here? What's the determinant of an upper triangular matrix? We just multiply the diagonal, right? So both of these calculations demonstrate linear independence of sine cosine. And then, sorry, what's my notation? Do I have, oh yeah, semicolon, the independent variable. So both these calculations demonstrate like linear independence. Just to be clear, the set cosine t, sine t is linearly independent on the reals. And we also have 1t, t squared linearly independent on the reals. There's no restriction on t here, right? The domain could be for all reals. All right, so Wronskian. Now, and I have, so some of you are like, determinant, what's the determinant? I haven't had linear algebra, how dare you? How dare you? Well, so here you go. These are the formulas for the determinant of a 2x2, a 3x3 matrix, and a 4x4 matrix. This is Laplace's expansion by minors. Here's how you calculate determinants if you didn't know already, just like that. These are the formulas. Can you turn the lights off again? Thanks. So if you wanted a formula for a determinant of an n by n matrix, there's the formula for you. Yeah? Okay. Here I've calculated the Wronskian of e to the ax, e to the bx, and I show that it's a minus b e to the... When would the Wronskian be 0 here? A equals b. Does it make sense that e to the ax should not be independent from e to the ax? I think it does. Those are the same function, right? Surely the same function should be linearly dependent on itself. Yeah? Now, I'm tempting you to think something you ought not think just yet, which is that if the Wronskian's 0, then they're linearly independent, linearly dependent. That's not generally true. For arbitrary sets of functions, it's possible to have the Wronskian 0 and yet have them be linearly independent. And the reason for that is subtle. It turns out you could have a different dependence in different parts of the domain, and in so doing, they would not be linearly dependent. A good example of this would be like the function x and the function absolute value of x, right? Those are linearly independent, actually, because they're not the same function. The absolute value function and the x function, they're different functions, linearly independent. And yet, when you calculate the Wronskian for those, well, that's troubling because you don't... I have to make a more interesting example than that because I can't differentiate the absolute value function at 0, right? So we can't even do this. So you take that example and you look at x squared versus x times the absolute value of x. X times the absolute value of x. Hopefully I have this written. Anyway, my point to you is just that the Wronskian can be 0. Here's some more. Look, here's an example where I actually do the 3x3 in all of its hideous detail. And this proves that x, cosh, and sinh are linearly independent if x is not equal to 0. All right. Anyway, let me not go on about the Wronskian being 0, being a subtle point. The point is, well, fine, I've said as much as I have. Oh! I'm sorry, I have to repeat to myself like 5 times before class. I will not talk about the Wronskian being 0. I will not talk about the Wronskian being 0. And I forgot to tell myself this before class, and so here we are talking about when the Wronskian is 0. This is a function, x squared. And you may not have thought about this before, but you could take, and I discovered this personally, I've discovered this formula in Roger Penrose's Road to Reality, which is a wonderful little book. And he talks about this function. It's a very interesting function, y2. Here's a formula for it, x times absolute value of x. So it's case-wise defined. It's x squared for x greater than or equal to 0, and it's minus x squared for x less than or equal to 0. And to casual observers, well, you can put equality in both. To casual observers, it looks like a cubic, but it's not. All right? It's 2 quadratics, half of a quadratic's joined here. And it is once differentiable, but not twice differentiable. This is a function, this x times absolute value of x, you can differentiate once, but not twice, because the first derivative gives you the absolute value function, twice the absolute value function. And then the absolute value function, we can't differentiate at 0 because it's got a kink in the graph, right? But you can calculate the Wronskian of these guys at x, and you're going to get 0. You get 0. Because either y1 is equal to y2 for positive x, or y1 is equal to minus y2 for negative x. But the thing is, it's a different linear dependence in different parts of the domain. So if you're talking about linear independence of y1 and y2 on a domain which includes both negative and positive numbers, technically speaking, they're linearly independent. And yet, the Wronskian is 0. So this is kind of maddening that it's the naive sort of reversing of the Wronskian calculation I just showed you doesn't work. We can't just glibly say, well, if the Wronskian's 0, they're linearly dependent for abstract sets of functions. The good news is that confusion is not damaging to you guys for the most part, because we like to think about solution sets. And for solution sets to differential equations, it is in fact the case that the naive thinking about Wronskians is true. All right, and that's what I'll show you next here. Oh, look, here's what I was just talking about. So x squared, x absolute value of x, you differentiate that, you get 2x, you differentiate that, you get 2 times absolute value of x. So the Wronskian works out to 2 absolute value of x squared minus 2 absolute value of x squared, which is 0. Yay. So just a cautionary tale. If you think it's confusing, that's okay. I have seen professional mathematicians not understand this issue and like answer from ignorance on the internet about this before. It's like people have not, this is a subtle thing that I'm talking about right now. Anyway, the Wronskian of a solution set of a linear ODE is so much nicer. And here it is. If we have L of y equals to 0, the homogeneous problem is an nth order linear ODE on the interval I, and we have solutions y1 through yn. If there exists a point x naught such that the Wronskian is non-zero at that point, then it's linearly independent. That's not subtle. That we already have proved if you go through what I did. But there's more. On the other hand, if there exists even one point such that the Wronskian is 0, then the solution set is linearly dependent on the interval. Now that's surprising. Let me show you why that's true. It goes to something called Abel's formula or Abel's formula, depending on where you're from. And here it is. So if we have, I'll derive it for the second order case because you can follow this, okay? So for n equals to 2, if we have a sub 0, a of x is not equal to 0 for each x and I, and we're thinking about the differential equation a0 y prime prime plus a1 prime, plus a2y equal to 0, if that has solutions y1 and y2 and I, we can calculate the Wronskian for y1 and y2. And the Wronskian for y1 and y2 is just y1 y2 prime minus y2 y1 prime. All right? And so something interesting happens if we calculate the derivative of the Wronskian. When we differentiate that, we got 2 product rules, which gives us 4 net terms. Some of these terms be canceling, right? Like this guy with that guy. These are functions, they commute. The multiplication functions commute. So that and that are the same thing. They cancel. And you're just left with like y1, y2 prime prime minus y2, y1 prime prime. Great. But then the thing is, y1 and y2 are not just any old function. They're solutions to the given second order differential equation, which means that we can rewrite the second derivatives in terms of the first derivatives in the function, because this is true, right? Y1, I can put a 1, 1, 1 there. I can put a 2, 2, 2 there. They're solutions, right? So that means I can solve for y1 prime prime like this, and I can solve for y2 prime prime like that. Then I can plug these formulas back up into the derivative of the Wronskian, and what's that give me? Well, y1, y2 prime prime, y2, y1 prime prime. And what happens when you do the math here? Well, some stuff cancels again, right? I get y1, y2, a2 over a naught. And over here I've got let's see, where was I? y2, y1, a2 over a naught, but I've got a minus minus is a plus. And over here I've just got a minus. So this term and that term, they be canceling. And you're just left with minus a1 over a naught